G'day Bifrosters. So today we're taking a look at some new compounds, a little bit more higher level compounds. This is the result of one of them. So this is a scatter on point, but I just thought I'd show you what it's capable of doing before we get into it. And please excuse my voice, I've got a bit of a frog in my throat, as it were. So how do we get from a single point to this? This is just a Bifrost in the plane, really. But let's go through that. So first thing I'll do is I'll stop Arnold from happening. We'll just go back to our viewport 2.0 and go to our default lighting. So that's what it actually looks like. And I'm going to show you how this is just a product of scattering on some points. Before we go anywhere else, let's just really quickly talk about points in a sphere. Okay, so I'm going to jump into the outliner and I'm going to hide this. I'm going to turn on our grid so we know where we are in the world. There we are. I'll draw your attention to the script editor here. Let's just pop the script editor in there for now. That's taken up too much space, and that's taken up too much space. So this is the beauty of Bifrost. So before Bifrost came along, if you wanted to make 1,000 points in a sphere, you would need to do something like this. It's getting there. It'll do it. I'm not sure when, but I can't parent things in the underworld apparently, which is always fun. But there you are. So that's a little metal script for distributing 1,000 points randomly in a sphere. It's not really slowing down Maya that much, but it took a wee while to happen, really. It took quite a while to happen. Now you can do the same thing, obviously the same thing in Python. Here you go. Enter the Bifrost. So let's go to our graph editor. And yeah, let's go back to our example here. If I want to put a bunch of points inside a sphere, I can put a spherical volume down and scatter inside of that. I can use the node I made. It's points in a sphere. So let's just let's take a quick look at that. Let's just go turn this off for a second. There we go. So what's going on in here, specifically inside this for loop, is exactly the same bit of code that was going on here. It's literally a transliteration of the Python code here. So I wrote this in Python, I based it on a website that I found, and I just went through and remade it inside of Bifrost as well. And you can see there's pi there, for example, random radius. So I just took this bit of code and Bifrosted it, more or less. And that's great. That's we've gone from null, which is arguably the easiest but also quite slow, to Python, which lets you, makes you write out the entire function, and now to Bifrost, where the function just runs, provides points. You can have as many points as you like. It's the big secret of scattering, and that's the big secret of Bifrost, is that you really just need to do something once. So if I take my points in a sphere and make it 1 point, let's fix that offset so we can see what we're doing. So if I change the seed, hey, that's interesting, isn't it? Obviously that first point there is one of the x-axis points, but anyway. What do I really want to do? Yeah. So if I scatter 1,000 points in my sphere, there we go. And I get one of those points from the array. 1,000 get point 248, which is that point. So you can see that depending on the seed that I'm feeding into it, this point could be anywhere. It's literally a point in a sphere. The only thing is within radius 10. So if I go radius 2, you're going to get the same deal. In fact, that's a much better way to show it. So that's a random position in a sphere, but it's always within radius 2 of the center. And so using this one simple idea, this placing a point inside of a spherical volume somewhere, you can go ahead and using what Bifrost gives you, you can build that up into that. So all of these points are based on a point in a sphere, a single point in a radius. Okay, so that's probably enough introduction. Let's go ahead and show you how this works. So let's see how we get from a single point to this. Let's go to points in a sphere. So now what we're looking at is this. And this is quite simply exactly what I was just talking about. It's a loop. If you jump in here, you can see here's the loop that generates the points. It's a loop of 15,000 points. It can be 25,000 points. Go to 250,000 points if you like. It's super fast. So I'm just going to really quickly run you through this and then we'll get on to the more interesting stuff. Basically, what this does is it scatters points in a sphere and allows you to change the distribution of those points. To start with, this is a very, very uniform sphere. This is scattered uniformly inside the sphere. You can change the way that those points are distributed inside that sphere. You can do it by curve. So you can see that there are a lot more points at the 0 position, and then they climb slowly to the outer position. So what happens here, if I just grab this, you can see how they're distributed. Pretty cool. Pretty simple. You can go the other way around, so they're all mostly pushed out to the edge, and this is between 0, or between the origin point, and the scatter radius. So change the scatter radius. Pretty simple. You've got a random seed, so just randomizes things. It's nice. You've got an offset so you can move them. So this is the offset of the center. You have a profile curve, which I've just demonstrated. You can do this by exponent, so you can have, if you go negative, it still works. Colors aren't very happy, but that's okay. You can see how exponent works. It's just basically multiplying each point's distance from the center by itself. So very, very useful for things like force and explosions and that kind of stuff. Then you have a Gaussian distribution, and the Gaussian distribution is a lot closer to what you might find in nature. If I was to show you what a Gaussian distribution looked like on this curve, we just pop that out there, just so that you recognize it. There's even a preset. That's what a Gaussian distribution looks like. It's the famous bell curve, or normal distribution it's also called. I've included it in this compound because you find it an awful lot in nature. You find it impact, and you get a lot of points around the middle, and less points as you go out. You got two distinct flavors of it, like so, Gaussian A and Gaussian B. They're just, one's sine-based, one's cosine-based. And then you can change the mean and the standard deviation. So you've got quite a lot of control over this. That is the big secret of scatter on point. And this is, we've taken one building block, which is the scatter points in a sphere, and now we've made another one. So now we have a sphere of scattered points. We can change our distribution, and we can basically make whatever patterns we need to make inside that sphere. And the reason that a sphere is super handy and super useful and used an awful lot is what I was saying before about things like explosions or weird growth patterns or whatever. You tend to get a lot in the middle, or impacts. You get a lot of things in the middle, and you get less and less as you go out. And having a way to visually control that, so doing something like this, it's fast, it's responsive, it's happy, and everybody's great. That's the big thing, is the distribution. The colours, they're all like, yeah, okay. Oh, that was a silly idea, wasn't it? The colours they look frivolous at first look, but you could also, for example, let's go for a power of 4. You could take this, grab the colour off the points, and use that as an intensity for something. So you've got more intense in the middle, less intense on the outside. You can also, of course, do that via a curve too. Like so. And then you can mess with the curve all you like. And your colours will go through. Pretty simple. And pretty nice. Those are the main controls. These just control the shape of what we're looking at. So there's spheres at the moment. We can see discs, points, cubes. You know how this works. Well, you may not. So I'm going to show you. The only thing I'm going to talk about with colour is this colour is profile here. So at the moment, that is a linear colour profile. So what comes in at 0 goes out at 0. What comes in at 1 goes out at 1. I can change that to these curves again. You can see the colours change. Let's just make it really, really obvious and reverse it. So they're dark in the middle, they're lighter the further out you go. And you might just get a better idea too if I go and turn that off. So we're not colour correcting on screen all the time. So you have a profile curve that does profile things. So this is just controlling the position of the points. And you have a colour curve, which controls the colour from the centre outwards. If I switch that on, what that is doing is it's getting the colour from here. So it's throwing that away, getting the colour from here. That's all you need to know about the interface right now. We're going to go to the next building block up in a second, like very, very quickly. I've spent too much time on this already. There's one more thing I want to show you. Let's get some cooler and funkier colours going. Something like that. Brighten the centre. Oh, it's probably still too bit bright. A bit too bright, isn't it? Do something like that. Cool. Whiten the centre, and let's get a lot of points. So let's go for 250,000 points. All good. We can take our very large number of points, and then we can start to cull them. This is an interpreted autoport. So this supports all kinds of float shenanigans. Single floats, so you can set a weight for every point, I think. Hey, let's try it. Not called float. I've been using Unreal too much. Value. It's a float. It's a float. 0.5. Put that in there. It's difficult to tell with this many points, but I think it's got rid of half of them. What this is saying is it's like there is a 0.5% chance of a point being created at this point in time, at this point in space. So if I say take that to 0.05, should have a 20th, 200th. And we've still got quite a few points because we started with 250,000. Keep going down. And even with this many culled, all of these still work. And don't you just love these sliders? Oh, so much better. So, but the thing with it being an interpreted autoport, of course, is that you're not limited to floats, float arrays, various other weird float-based concepts. You can also stick a field in it. And this is the nice thing. I believe that the field is delivering as negative 0.5 to 0.5 range. Add 0.5 to it. But of course it's a field. There we go. So now this is delivering, I believe, 0 to 1 range, which is what we want. And then we can start changing things. Number of frequencies, so how complicated that field is. The frequency itself, you can have many less, or not that many because things start to fall apart. So clumps and lumps and various other things. And because this is a field and it's spatial, you can watch this change as you move it. I'll just drop the frequency to give you a better idea. So you can do all kinds of very nice things. And not only that, you can evolve the field over time as well using this plug here. There we go. I'm going to stop talking about this one now, because this is just another stepping stone on the way to the next one, which is when we scatter on points. That's where we can start bringing in some more advanced things. This is where we leave scatter on point and we move over to look at scatter on points. And here we are, looking pretty familiar, isn't it? That's because this is the real power behind Bifrost. You can start with one thing that's kind of cool and work all your way up to something that's really cool. So the cool thing was I can put a point anywhere within a sphere. This is where it's taking me to. The only difference between scatter on points and scatter on point is this. So you can have all of the points the same size, same scatter, same seed, everything. So they're all going to change at the same time. They're all going to have 20,000 points or 20 points or 200 might have been better. They're all going to be uniform or curve or whatever, so they're all identical. But if you turn this on, then you're going to get a random each time, which is great, especially for if you want to start doing some things like scattering. So I don't need to go through the interface with you. Really, all I need to do is I need to show you how to make something with it. Because everything else is the same, including 200,000 points per point coming in. Oh, by the way, sorry. This is just a dummy point generator. So this is generating 10 points. I can generate 5. That's fine. I can put a different seed down. And that's fine too. You can even slide it. There you go. Quite nice. It's a little bit laggy because I have a million points on screen right now. It's 5 of these, 200,000 each, and they're all different. So this is just what's providing the points to start with. I can turn these guys off and turn these guys on, and probably need to just turn off the terminal as well. Change the backdrop color, so that might be a bit easier to see. Just overcook that color a bit. There you go, there are your random points. So that's all that dummy points is doing. It's no different than you doing a random value array on a vector and spitting that in there. There we go. And we'll hook these up again because I can't get over how cool this is. Thank you, Jonah. So this is all very well and good and, you know, fairly tasty and good looking. But let's do something a little more practical with it. I'm going to really quickly take you through making the example. So, I already have the example use shape, and this will be included. You'll be able to have a look inside here, read the notes, and try and, that's not part of it, try and sort of work your way through it. But really, it's the same thing. It's scatter on points. It's the main scatter here. I've even included the dummy points and the fractal noise field if you wanted to play with that. The big difference here is with scatter on point, it would give you the positions, the normals, and the colors, which is fine. Let's just jump back over to this guy for a second. So if we just had a single one of these, we used a scatter on point. What's coming out is the positions, so obviously the point positions, the points themselves, yeah, which is cool. as a point cloud object. The positions, the normals, the colors. So this is just sending out all of these arrays. What's different with scatter on points is that it's also including the local center distances. And that what that means is that that's an array that stores the information how far each point is from its local center. So its local center is what's coming out of here. So this is just storing how far each point is from that local center. And that's going to become very useful later, as you can see over here, when we do some cool instancing. So let's just real quick, what I'm going to do, I think, to make this the easiest is we'll hide that, grab that guy and duplicate him. Show that. So it's the same thing, same graph, I just duplicated it, and let's just start breaking connections so things don't work anymore. There we are, we've just lost our points. And that's all fine, that's all that stuff up there, surfaces and everything. That's the terrain. And if you're interested in how I made a really quick terrain like this, the terrain is generated by this fractal noise field displacing the points of this plane. But the reason it looks more like hills and valleys and things like that is just what this is doing to it. So it's really just allowing me to play with a curve. That allows me to flatten things and stuff. So anyway, yeah. So from out of that, we're generating the arrays, we're generating the arc color, which is really just for the viewport because there's a shader on it. And we're generating the raycast directions, which we will use in here. So let's throw down a terminal like this. And we're not going to need that just now, but we'll just turn on these points. As a think for a second. They're all very colourful and very big and very weird, so let's go in here. Let's change this value. So they're a bit bigger, we can see what's going on. So you can see that I have, in here I have 24 dummy points. Look for the light values here. 24 dummy points. Between minus 15 and 15. These are the points I'm scattering on. And then scatter on points, I'm throwing 100 points. I'm scattering 100 points on each one. Like that. Which is cool. Letting it do its thing. And then what I'm outputting is the point cloud itself into merged geometry. Because it's actually giving you 24 point clouds in there. Just merging them all down into one. Why is it 24? It's 24 because I told it to be 24 with my dummy points. Right. So the points in here control this. This is a big loop. There's the current index there. Great big loop. So the points in controls the number of times around the loop it goes. So anyway, the upshot of it is we've got new geometry, which I've gone to get point position now. I could also have gone out from here, flattened the array like I've done here. So that just flattens the 24 arrays coming in down into one. And that way I've got this number of positions and this array is the same. So each one of these bits of data corresponds to one of these positions. What I'm doing then is I'm taking these and I'm raycasting them down onto this terrain. I'm using get raycast locations. I'm using a line, not using a cutoff distance. I am sampling the point position of the terrain surface, which is awesome, and then I'm just outputting that. So if we hook that up, you can see how this works. So what happens here is we need that one to go into positions, and we need this thing called directions, and that's an array I'm making up here. And all this is doing is it's making a new array that is pointing straight up. 0 in the X, 0 in the Z, and 1 in the Y, it's an array pointing straight up. And I'm using that for the directions, so let's plug that in. Cool. And then I need the terrain geometry, which is this guy. I'm going to pull it out of this pass for tidiness. And I need the points geometry, which is the merged points. So let's move our handy terminal. We'll turn off our points for now. And this is going to be the points object raycast down onto that surface. So let's take a look at that. Awesome. So you can see those are the points, but they're projected onto this geometry. So they're all sitting on the surface of the geometry. And because Bifrost is super awesome and powerful like this, I can go ahead and change some stuff in here. Like I can change the seed of my dummy points to 900 and my points would change. Super awesome, non-destructive, all that workflow stuff, really good. And I can do the same in there and change the amount of points. Change the seed here as well, so and the patterns will change. Now I'm scattering these as a curve right now. I can change that. I can scatter them as Gaussian. So this would be like if you dropped an awful lot of very, very fragile rocks from a great height, and they all broke into pieces, which magically got turned into something else. But increase that scatter radius a bit, and I'll increase the standard deviation a bit. So you can see there's still more in the center than there are on the outside, but they're just a bit better spread out now. Cool. So what I'm doing now to increase the power of this whole thing, I mean, my goal was to go out and use this, and I didn't use it in the most realistic scenario. You don't usually get rocks halfway up a hill, or in this case like a little bumpy bit of mud or whatever it is we're doing. I wanted to use the scatter on points in a situation where it could be used, and this is one of them. Obviously you could do things with the density weights here. You could say, well, hey, I mean, I need all the heights of the terrain, and if you over there are above this height, then just don't scatter there, please. Then your weight would be 0. You can do all that kind of stuff, just like you can with the scatter pack, and it'll obey it and do it, and everything's cool. But for now, what I've got is I've got a bunch of points scattered on the terrain. So you can see this 3D, it's the third dimension. So the points are 3D scattered. Well, technically they're projected downwards, but that's okay. Houdini has ray, we have raycast, it's great. What I'm doing then is I'm just generating some rocks, basically. So let's have a look at those rocks. They're not the world's most realistic looking rocks, but they're just a bunch of rocks. And I'm just doing that with a sphere here, looping through that sphere and displacing it by a fractal turbulence field with a different seed each time. That's really quick and really, really filthy, but it works. And then inside here, I'll just lay that out. We're creating an instance. We're using the points coming in from, let's turn that back on. So inside here, the points are coming in, and those are the points that we've got in white. The rocks are coming in, and they're being instanced on top of it, randomly. And I'm just scaling them, giving it a bit of a random, and randomizing the rotation. And that's what that looks like. So turn that off, turn that off. There are my points. There are the instances on top of it. Now there are some don't match. They may have been scaled completely out of existence. But you can see, if you look at this cluster here, I turn that on, there they are. Ah yes, local distance from center. Even if I scale these all the way out, the ones furthest away will either be very, very tiny or not there at all. Because local distance from center goes from 1 at the center to 0 on the outside. So if we wanted to absolutely have every single rock that we scattered, we'd need to do something like a change range, that coming in. Now I believe this is from 1 to 0, so let's try that. to 0, to 1 to 0 point, I don't know, 2. There, all of those rocks turned up. Which is great. It's probably something I should have done anyway. But I mean, I can also make these bigger, make them smaller. I shouldn't be messing with the start value actually, because it's not going to be good for me. I should be starting with this. So you've got a lot less variation now, but you've got all of the rocks turning up. 0.1 will still keep the rocks, I think. Starting to lose the very, very furthest ones out. But there we go. You are now getting every rock has its point, and every point has its rock. Like I said, it's not the world's most carefully crafted scatter, but it does prove that it works. So at this point, we're done. So I can get rid of these two here, because they're just for me showing off. And then I'll hook this back up. And if we took this a step further, which we could start to do things with the culling like this. So if I plug in my fractal, as I think about it, you can see it's cleared out an awful lot of those rocks now. And because, like I said, because it's non-destructive and procedural and all kinds of lovely, I can just change this. And it changes pretty much in real time. There's nothing wrong with that. I mean, this is a really quick way to iterate. You don't like that scatter? No? Yes? I like it? I don't like it? Things aren't in the right place. Can you change it? Of course I can change it. I can change all aspects of it really, really fast while you look over my shoulder. And you can change any aspect of it you like, almost at real time. Now, I mean, granted, I'm not scattering that many points. If I was to go, say, to 2.5 times that, then we can mess with the fractal some more. And even without putting in like a mask based on height or something like that, I'm starting to get something, you know, fairly good looking just by itself. And that's really the power of this. And it'll be something that we highlight again and again in these videos as we go ahead with the new compounds that we want to show. What I wanted to illustrate, and there will be more of this coming, is just how you can start with something really, really simple and build it up and build it up. You're running that simple thing in a loop and generating stuff with it, and then you're running that loop in another loop in parallel to get something like this. Anyway, that was scatter on points. Keep your eyes peeled. There should be more coming. Just remember, you can build really cool things from one really boring thing. I'll let you get on with your night. Thank you very much.